recall what the equation of an ellipse is which is centered at the origin. If you remember, it is x square by a square y square over b square. This is equal to 1. So that's the equation of an ellipse. And as you can see that if you scale the x and y coordinates appropriately, you can absorb the a and b into the coordinates themselves, and that will become an equation of a circle. So you can turn an ellipse into a circle by scaling the coordinates, x and y coordinates, appropriately. Okay. I want to so let me draw this ellipse first. That's our x-axis, y, and okay, so this is our ellipse. It has focus here and there, okay, and the focus is at this length from here to this place. It's not looking very symmetric, but it's okay. This length, if I call f, this is at a square minus b square square root. Okay, and because a is going to be greater than b for us, this is fine. Okay, and this point is a. So this is 0, that is a, and this point is b. Okay, that's fine. And our focus f is at minus f comma 0. So I'm looking at this one right now. Okay, that's good. Now I will call these x and y coordinates as x0 and y0. Okay, so these, instead of calling them x and y, I'll call them x0 and y0, because I want to shift my coordinate system to here. So I want to shift the y-axis to this point. Okay, so my new origin is here at the focus, which means that you should do the shift of x-axis to new x according to this relation. So you can see, if when x naught is minus f, your new x is 0, so which is correct. So your origin is here now. And to get the equation in polar form, all you have to do is substitute this in here, and then use the polar transformation. So also let me write down this. So you get x minus f, where f is given by this relation, whole squared 1 over a square plus y square over b square is equal to 1. Okay, next you put x is equal to r cos theta and y is equal to r sin theta. So what you're doing now is you are measuring things from this origin, new origin. This is your origin. Let's say the distance here is r, and if you drop it, this horizontal distance is r cos theta and the vertical is r sin theta. Okay, that's all you have to substitute, and then you solve it and you get two solutions. You get r equal to minus b square over a plus a square minus b square square root cos of theta. That's one solution. And the other solution is r is equal to b square over a minus a square minus b square in the square root, this entire thing multiplied by cos of theta. Okay, that's what you get. We can we can rewrite this as the following: minus b square over a. You can write it in a nicer form than what I'm going to write here, but it's not necessary for me to do that. You get 1 plus epsilon cos of theta. I'll define the epsilon right straight away, and here you get b square over a 1 minus epsilon cos of theta, where epsilon is 1 minus b square over a square. Okay, and it is called eccentricity. Okay, let's look at this. If b is equal to a, then epsilon is equal to 0, and eccentricity would be 0. Okay, and your ellipse will transform into a circle. So it is not at all eccentric. It looks same in all the directions. That's what you get. Okay, now let's ask. Yeah. So okay, so these are the polar forms of your ellipse, and we can simply write down without worrying about what's in the numerator. Of course, that can be related to other quantities which characterize an ellipse. So you have the following form: 1 minus epsilon. R is alpha over 1 plus epsilon cos theta, or R is equal to alpha over 1 minus epsilon cos theta. You see, you have two numbers which characterize the ellipse, a and b here. Okay, but this epsilon does not know about a and b separately, only knows about the ratio. Okay, so if you had, let's say, taken a and b to be something, if you make a 10 times and b 10 times, okay, epsilon still remains the same. Okay, but then you have the other thing which is in the numerator, which knows about other variable also. Okay, because it does not have a square, it has a. Okay, so that way you can determine both a and b if you know epsilon and what you have in the numerator. Okay, so let's ask what these ellipses look like, and I will tell you what they look like. So this ellipse looks like this, and that's how we have constructed. We started with this. Okay, this is one of the focus, and this also looks identical to the one I have drawn just now. Okay, you get the same thing. Okay, so it's clear. If you put epsilon to 0, you get a circle, as I said just now a minute back. If you put epsilon to 1, you get a parabola. Let's go back and see. You see here, this is 1 plus cos theta or 1 minus cos theta and something in the numerator. Okay, so epsilon 1 will give you a parabola, and epsilon between 0 and 1 will give you an ellipse, and if you put epsilon greater than 1, you'll get a hyperbola that you can check. Okay, this is all I would remind you about ellipses, but to encourage you to use some programming language to once in a while do calculations using them, I will show you a small calculation which I did before preparing this lecture. So I have solved this equation here of this one and obtained these results, these two, in Mathematica. Okay, and as I said before, you don't have to learn for exam, but it will be nice if you do so. So here I have written a program which is not necessarily in the written in the best way, but it works. So I have defined my f here is a square minus b square square root. Okay, that is the distance of focus from the origin. Okay, then I am calling something expression expr is expression 0, and I say x0 square over a square plus y0 square over b square, which is what you had here. Okay, x0 square plus y0 square, and both are divided by a square and b square, and then you have a 1. So that's what I'm writing here. Okay, and then let's go back, and then this slash dot means I'm going to substitute, see this slash dot, this thing here, that's the syntax. I'm going to substitute x naught to be x minus f and y naught to be y. Okay, and whatever you get in that, I again further substitute x to be r cos theta and y to be r sin theta. Okay, theta is being called t right now, and this cos and sine, these are user defined, so these are not really cos and sine functions in Mathematica. They have to have capital C and capital S. Then I defined a new expression in which I will take the previous one and substitute sine square theta to be 1 minus cos square theta. And then whatever I've got, I'm solving that expression. So you see, if you write down the equations on the sheet, on a piece of paper, you'll find that what you have to solve is the entire thing which I have written above, that equal to 1. That is your equation for the ellipse. So that's what you want to solve. So I've solved this and simplified a bit. Okay, and after simplifying, I get the following result. This, so it gives me two results: r equal to minus b square over a plus this thing times cos t, and r equal to b square over a minus this thing times cos t. Okay, I have just extracted out the first piece. I could also remove the curly brackets, but I have just copy pasted next. So I'm putting a equal to 2, b equal to 1. We wanted to choose b to be smaller than a, that's why I have chosen these numbers. And I do a polar plot, which I was talking last time. Okay, I've just taken this piece and put in here, and I vary theta from 0 to 2 pi, and that's what you get. Next, I have taken this piece, the second one, the second r, and plotted it here. You see, you have a minus sign here, and then this is the second piece. It gives you the same ellipse as I said. Next, what I have done is I have taken the expression which you have here, okay, and just remove the minus sign and plotted, and you see you get the ellipse, but this time its focus is here, and the ellipse is going to the left instead of going to the right as here. Okay, that's the only difference. So if you change the sign, this is what you get. Before we leave ellipses, let's look at how ellipses change as you change the eccentricity. Okay, this is again a very crude way of doing things, but easy to understand if you have not already learned programming, Mathematical programming. So I have chosen different values of epsilons, eccentricities here. So I have chosen E1 to be 0, epsilon 2 to be 0.4, epsilon 3 to be 0.6, 0.8, 0.9, epsilon 6 to be 0.94. And if you take epsilon to be 1, you should get a parabola. So this is very close to being parabola. So let's see. And here I am just plotting r. I am defining r1 to be 1 over 1 plus epsilon cos t. Okay, and these different values of E1, E2, E3 and E6, they will control the eccentricity of ellipses. right? Now I'm trying to do a polar plot of several of these. So I have R2, R3, R4, R6. They are all have to be included within a curly bracket here, and I'm plotting from 0 to 2 pi, and I should put a show here so that it can show all of them together. And this is what you get. Okay, the same image I have zoomed now, and this is what you get. So you see, even when you are very close to 1, your epsilon is 0.9 or 0.94, you are still not getting a highly elliptical thing. It's, you see, this is what you are getting. So this is how this eccentricity grows. And let's see what happens if I put epsilon to 1, you get a parabola, and also epsilon greater than 1, you'll get a hyperbola, and that's what I've done here. So I've defined another R8 and R9. You have E8, E9, which I've taken to be 1 and 1.1, and you see this is what you get. Okay, so this blue thing is the parabola here, and then you have the hyperbola. Okay, the two parts of the hyperbola here you can see. Okay, so now you know what the form of conic section is in polar coordinates. It is just r is equal to alpha over 1 plus epsilon cos of theta. Okay, good, that's where we will stop, and now we will continue with our Kepler problem.